We have now made it to chapter 4. I know we spent a little bit of time talking about categorical data. We've looked at bar charts and pie graphs, and now we're going to move our focus to the second set of data that we want to collect, and that is quantitative data. So we see that we have a long list of homework problems, and this is quite a large chapter. So stay with me. I'm going to break this down into probably 3 videos. And this one, we're going to go to slide 26, if you're following along with the notes. Our objectives for chapter 4 are students organize and describe distributions of data by using histograms, bar graphs, dot plots, stem and leaf plots, and box and whisker plots. Some of those you may be familiar with, but I'm going to show you each one of those and how you can create them. Secondarily, students will calculate the mean, variance, new word for many of you, standard deviation, median, range, and interquartile range, better known as IQR, of a distribution of data values. And then chapter 5 will do even more with quantitative data before moving into the normal distribution. So when you are dealing with a lot of numbers, it's important that when you're summarizing the data, you give a sense of what these large data sets are behaving like. So if we're looking for the behavior of large sets or distributions of quantitative data, the first thing any statistician or researcher should do is to make a graphical summary of the data to get an overall view of the data distribution. We want to see what is going on here, which is why I say again and again and again, you will make a picture, and make a picture. However, we cannot use bar charts or pie charts for quantitative data because that is exclusive for categorical data. So what do we use? Well, we use histograms. A histogram is much like a bar chart, but with a significant difference. And that difference is there are no gaps between the bins in a histogram because the histogram displays a continuous graph. So everything is connected. If there are gaps, they're there for a reason, as opposed to with a bar chart, gaps are there to separate different categories. So to draw a histogram, first, we divide the entire range of data values covered by the quantitative variable into equal width intervals to be represented by bars, which we will call bins. The bins and the counts in each bin cover the entire distribution of the quantitative variable values. Now, I want you to shoot for 7 to 15 bins. If you have too few and the picture is not revealing, it's just a few boxes. If you have too many bins, the picture becomes too complex. We cannot see the forest from the trees in this situation. So the information you wish to communicate will help determine the appropriate number of bins. With a histogram plots the bin counts as the heights of bars. So same as a bar chart. So with a histogram and a bar chart, they're not the same. So don't get these confused. A bar chart has gaps between the bins, which are the categorical data. A histogram has no gaps between bins reflecting the continuous quantitative data represented. A histogram provides a graphical representation that illustrates the shape of your data distribution. And we are going to do this over and over this year with quantitative data. So I want you to get used to making histograms. If we look to the graph on the right, we're shown a histogram of HDL, which is your good cholesterol counts. The higher values are the better ones. If you look at the bins are labeled with integers, but represent an interval because we have ranges of values. So this 31 represents not just 31, but numbers from 30 and a half to 31 and a half. And then the vertical axes show our counts of the number of measurements we had with 20 to 29-year-olds with HDL cholesterols. Now notice, we still have a title at the top. We have our axes labeled in terms of frequency and what the variable is in this case. Always label your graphs. Again, if we wanted to look at a relative frequency histogram, this will display not the frequency, but the percentage of cases in each bin instead of the count. A relative frequency histogram looks identical to a frequency histogram. The only change is the vertical axes scale. So if we look to the right, again, we're looking at cholesterol level. and now we see relative frequency, and we're looking at the percentages. Here is a relative frequency histogram of overall cholesterol levels, and it's different than the HDL. Only the one aspect, the relative frequency or the percentages, changes, but otherwise they're indistinguishable. The histogram is a graph that displays the data by using bins, or bars, of various heights representing class frequencies. The histogram bins are contiguous, so there's no gaps. And I want you to remember this. Gaps between bars equals bar graph. If you think gaps, and they're always there, that is a bar graph, not a histogram. With your horizontal axes, the lower boundaries or lower limits align with the sides of the bins. The midpoints of the data classes align with the center of the bar. Vertical axes show the height of the bar represents the frequency of each class. So we have classes, and we have classes or bins, and then the height will give the frequency. So a grouped frequency distribution is used when the range of data values is large. The data is grouped into classes that are more than a single unit in width. Class limits represent the largest and smallest data values that can be included in a class. Class limits are actual potential data values. Class boundaries, on the other hand, provide the values that eliminate gaps between the classes in the frequency distribution. Class boundaries are 1 decimal place more accurate than the data, and class boundaries are not potential data values. This is how we separate out our classes or our bins. The class boundaries are typically 1 decimal place more accurate, which is the average of the upper and lower limits of the adjacent classes, and are not actual data values. The class boundaries are the result of the interval of each datum represents. Okay, so let's actually build one of these to see what we're talking about here. When we're talking about class width can be calculated by subtracting successive lower class limits or successive upper class limits or the upper and lower class boundaries. With the class midpoint, we'll just call that x sub m, can be calculated by averaging the upper and lower class limits or boundaries. So that's how we get our midpoint to graph each one of these values. So if you had the lower limit and upper limit, let's say they're 10 and 14, 10 plus 14 divided by 2 gives you 12. That would be your midpoint where you would put your class bin. So here are the rules for creating a histogram. We want no overlapping intervals or classes. The classes must be mutually exclusive, which means nothing in common, and exhaustive. Every single number that is in our data set will be in that class. One datum cannot belong in 2 classes, and all potential data values are included. Number 2, class widths must be consistent. You cannot have your first width be, let's say, of 20, let's say 0 to 20, and the next one be 20 to 30. Everything has to be consistent. The class width should be small enough to accurately portray the data, but large enough to keep the number of classes manageable. Think about who's looking at your charts. Readers of the data cannot assimilate too many classes. The forest gets lost from the trees if there's too many bars going on. So the number of classes is best kept between 5 and 15. Fewer than 5, and you lose all trends in the data. More than 15, and the information becomes lost. This rule is not cast in stone, though. So I try, in general, to limit between 7 and 12, depending on the data set. 4, the whole idea of a frequency distribution is to provide an accurate and easily understood picture of the data as simply as possible. You want someone to be able to look at your chart and understand what this data set represents. If the class width is an odd number, the midpoint of a class is an actual datum value. That can be useful for a graphical representation of data. Not a necessary condition, but often useful because we like pretty pictures of our data. So, with a grouped frequency distribution, this is how I would like you to proceed. Find the highest and lowest values in your data. Next, find the range of the data, which is highest minus lowest value. Next, we want to select the number of classes desired. Do we want 7? Do we want 12? And that will depend on how many values we have. Find the value of each interval by dividing the range by the number of classes desired. So if our range was 35 and we wanted to have 7 classes, we would do 35 divided by 7, which would give us 5. If the result is not an integer, select the next largest interval. So if instead our range was 34, for instance, 34 divided by 7 is 4.8. And then what we can do is simply round up to the nearest integer. Next, select a starting lower limit, usually the lowest value. Add the class width to get successive lower limits. Next, we will find the upper class limit, tally the data, and record the class frequencies. So let's take a look of a set of data. This is where you'll need to take out a calculator. And as I get my calculator set up, what we want to look at here is the following data represents the record high temperatures for each 50 states. If you would like to do this on your own, great. If you would like to watch me do this, then I will show you how to do this on a TI Inspire. So if you have a TI 84, simply hit the buttons at the bottom of the screen, hit the stat button, edit, select, and then enter the data list. So we are going to go about constructing your data set. Now on my TI Inspire, I'm just going to click the list of spreadsheets from the bottom, and you can see that I've already typed in this data. Trust me, there are 50 values. What you need to do is go to the first thing, always give your data set a name. So I'm going to call this temps, and I have values 1 through, just so you can see, 1 through 50 for each one of our 50 states. Step 1 is determine the classes. So once we have the classes, we need to identify the range. Now there's 2 ways to do this. First off, you can look at the data set that you're given, and you can see the lowest value is 100, and the highest value is 134. So the difference between those two is 34. If you're looking for the width, and we want to say 7 classes, we'll take 34 divided by 7, which is 4.8. We round 4.8 up to 5, because that is the next greatest integer. On your calculator side, once you have all of your data values typed in, if you hit the menu button, and then we go to Actions, and you go down to 6, or type in Sort, you can take your data values, which are unorganized, and organize them, either in ascending or descending order. So we're going to sort column A, that's the one that we have data in ascending order, and I can hit OK. And now everything goes from the lowest value all the way to the highest value, which is a fast way of being able to find the range of your data set. So now that we have the class size of 5, next we choose the lowest data value, which is 100, for our initial class limits. So we are looking for all of the values to include for our 7 classes. So we would have 100 to 104. That's 5 data sets. Sorry, 5 temperatures. Then 105 to 109, 2. Then 110 to 114, 115 to 119, 120 to 124, and so on and so on. The subsequent lower class limits are found by adding the class width to the previous lower class limit. The initial class upper limit is 1 less than the succeeding class lower class limit. The subsequent upper class limits are found by adding the class width to the previous upper limit. So if you did lower limits are 100 plus 5, 105, and then 100, 101, 102, 103, 104. That gives me my lower limit, and we have our gap in between. To determine the class boundaries, where we're actually going to construct our histogram, The class boundaries are the midway point between an upper class and subsequent lower class limit. So if the gap between the class limits is 104 and 105, obviously our boundary is going to be halfway in between, 104 and a half. So now we can start sorting how many values fall into our classes, knowing that our class boundaries are 1 decimal more than our possible data values. And then we look from our chart to count the frequency. So we have 2 temperatures between 100 and 104. And then each one, we count the values of how many record high temperatures fall in there. And then we can also calculate the cumulative frequency to make sure that we've included all of our data values. And this is especially helpful when you're doing something by hand. Then we're going to go about constructing our histogram. So our largest value of frequency is 18. So our highest value is going to be 18 on our y-axis. We're going to label our y-axis frequency, and we're going to count by 3s. So we have our first class limit is 99.5 to 105.5. Then 109.5, 114.5, 120.5, 125.5, 130.5, 135.5. Those are our class boundaries. And then in there, we are going to put our bars. Now, if you think, what is the midpoint between 100 and 104? That would be 102. And that is where our middle value for our first bar is. And then subsequent, each time we get our histogram distribution for our data. Note the limit boundaries. We still have a name for our label, our axes, and we have a name for our chart. It's important that we always remember to add each one of those. Now, if we want to get real here and use the calculator to draw the histogram, we are using data entered from our list. So we've entered the data, and now if you want to follow along for your TI Inspire, follow what's on the screen and in your notes. If you're on your TI Inspire, what we are going to do is we're going to hit Control Doc, and we are going to add data and statistics. What we are going to do is we're going to click Temps, and now we see this is a dot plot, and we are going to hit Menu, Plot Type, Histogram. Now we see our bars. What we want to get a little more specific on is our bin width. So if I hit Menu and I go to Plot Properties and I go to Histogram Properties, I want to go to Bin Settings, and I want equal bin width. So our bin width is 5, and our alignment is going to be at 99. Let's say our lowest value is 100th. So if I hit OK, we now see, if I scale this down just a little bit, we get the exact same distribution. And all I had to do here was scale this down. But again, you could go Menu, Plot Properties, and you can change any of the scaling that you want. Okay, back to the notes. Another way of displaying the data in a similar fashion is a stem and leaf plot. A stem and leaf plot shows the distribution of a quantitative variable like a histogram does, while preserving the individual values. Now, you might have seen a stem and leaf plot way back in 6th or 7th grade. And so we're just going to refresh your memories on that. A stem and leaf plot display contains all of the information found in a histogram, and still, when properly created, satisfies the area principle and shows a picture of the distribution if you just turn your head slightly sideways. So if I compare the histogram and stem and leaf plot for pulse rates of 24 women at a health clinic, note the stem and leaf plot displays the shape of the distribution while retaining the actual data values. So if you're looking to identify what the mode is, then a stem and leaf plot is a lot more handy. If you're looking to construct a stem and leaf plot, first, cut each data value into the leading digit, which we call the stems, and the trailing digit, which are the leaves. Use the stems to label the bins. Now note, if you only use one digit for each leaf, either round or truncate the data values to one place after the stem. Because, just like we had with a histogram, we don't want our bins to be overly full. 5 and 6, 6, 0 would be 60, up to, this would be 55 through 59. This would be 60 through 64. This would be 65 through 69. Then 70 through 74, 75 through 79, 80 through 84, and 85 through 89. This is what we mean by stem and leaf plot. We take the tens digit followed by the ones digit, and we see that we have 4 values that are at a pulse of 68, or 4 values that are 72. The thing that people forget, and I want to emphasize this, is that you have to include a key. For every stem and leaf plot that you create, you always include a key. So what does this value mean? There are too many smart people that take this class, go onto the AP test, are asked to create a stem and leaf plot, create it beautifully, and forget a key. They automatically lose a point and they cannot get full credit. So when you're creating a stem and leaf plot, first, we want to take all of our values and write them down. So I'm going to fly through this, but you can see that we go 0, so our single digits, 10s, 20s, 30s, 40s, 50s, 60s, and 70s for this data set. And we're just, if you record them as they're written, we have 9, then we have 7, and then we have 18, 15, 16, 22, 12, 10, 18, and 5, and so on and so forth. So if you just write these values first as they appear, you need to write them next, if we want them to be properly displayed, in ascending order. So instead of writing 9 and 7, we write 0, 7, then 0, 9, then 10, 12, 15, 15, 16, 18, 18. This gives us a better representation of the data while still including our key. So this is worth practicing, because if you need help making a stem and leaf plot, just ask. It's been a while. Last, what happens if they're not digits, but rather decimals? How can you arrange these values? Well, just like you do a number. So if we are creating a stem and leaf plot from this data set, we can use our digits, so 6 point, 7 point, 8 point, 9 point, 10 point, 11 point, and 12 point, whatever the decimal is, provided that we enter our key for these values. So the way you would read 6.2 would be 6.2 in this case, and not 62. This is why a key is so important. So we give some context to what our data is representing. Last way to display quantitative data that you'll see here are dot plots. So a dot plot is a simple display. For each case in the data, simply place a dot along the x-axis. We've seen this in class already. The dot plot to the right shows the Kentucky Derby winning times, plotting each race as its own dot. Now, when you can see what's happening here, you might see a dot plot displayed horizontally or vertically. My personal preference is a horizontal axis, but we work with what we can. And if I asked you, what's going on here? If you had to make any conclusions, we have one set of data that's between 150 and 162 seconds for the winning time for the Kentucky Derby. And then if you go further down, we have this second set of distributions that are much faster times, which leads you to ask the question, what's going on here? Why is there such a large gap between the horses that ran the race between 150 and 165 seconds versus the horses later on? Think if you can figure out why that would be the case. Lastly, and this is the end of the video for now, end of part 1, I need you to think before you draw again. So remember how we start with make a picture. Now that we have options for data displays, you need to think about which type of display to make. This is the human nature for statistics. Different graphs emphasize different aspects of the story. So before you create a graphic display of your data, be certain you match the appropriate type of display of your data and that the display illustrates the aspects your data that you intend. For quantitative data, use a histogram or a line graph, stem and leaf plot, box plot, or dot plot. For qualitative or categorical data, you use a bar chart, pie chart, or dot plot. That is it. So we're going to pause here. Next up, we're going to look at how do you analyze a histogram or a stem and leaf plot or quantitative graphical representation, and how you can use these 3-4 letters to give me the description of any graphical display. See you in part 2, Falcons.